Hello, it's Keith here, and this is lesson 2 of the Photon series, and Photon is of course my little Tron clone. It's just a simple vector-based game in which we play a little dot and we have to try and kill other little dots. Not much fun, but it's a curious little project, and the point of the game was really to try and make a game with different kinds of graphics, because Yquest used tiles and sprites and things like that, but Photon of course uses pixels. Now on a system like the BBC that's not too bad, but on some systems, though they're tile sprite based systems, it's quite challenging indeed. So that's what this series is really covering, how to use pixel graphics and how to essentially write a PSET routine and a point routine on a wide variety of different systems and have them work in the same way, because this game is the same game running on all of these different systems. 90% of the code, more than 90%, is identical, and it's just a small bit of code on each one to handle the point routine for reading pixels, PSET for writing them, and the joystick routines, which are the same as the ones in Yquest. So this game was pretty quick to port, fortunately, and that's how I'm able to make so many videos. Okay, let's go over to the source code and let's take a look. So this is the BBC version of the game, and we've got some settings at the start which are defining the settings that this version of the game needs, because some things change each system. For example, the BBC has only 3 colours. I'm not counting black, the background. It's got 3 colours. Some systems have 4 colours. This one doesn't. So we're mapping colour 4 to colour 1, and that's basically just getting around that limitation. So that's one thing. And we're also defining the screen size. BBC, I tend to use the BBC first because it's got a screen quite similar to the Amstrad CPC in a lot of ways. So it's got 320 pixel wide screens, so we're using that 320 pixel wide screen, and that's why we've got these definitions here, just to set the boundaries for when we're drawing the screen and also the scale for when we're drawing the title. So that's what we're doing there. And we've got a definition for the user variables. Now you'll notice there's some stuff here. I am using conversion. I use some scripts to help me convert my Z80 code to 6502, and I use some macros to simulate some Z80 functions. I know some people probably don't like that. I understand why people won't like it, but there's simply no way I can write this many tutorials on this many systems this fast and not go completely insane without trying to cut some corners. So I'm afraid I have to do that, otherwise I just couldn't make these tutorials anymore. So yep, that's what those are there. Now here at the start of our code here, we've got some initialization here. We're just turning, the emulator seems to make a sound at the start, and I just need to stop that there. And then we are actually relocating our code to a new run address here. So we're moving it from 3000 to memory address 200, and that's because we need more memory for the video screen. That's what's going on there. I think I've done that before in my other tutorials. I can't quite remember. And then we're turning on the screen here, and we are using the config, which you can see down here. So this is the shape of the screen, the CRTC, which is ironically the exact same one as the CPC, which is obviously why I like the BBC, I guess. And then the color definitions here, and there's 4 for each color in 4-color mode here. So you can see these, and these are defining the 4 colors, and the colors are black. They are cyan, magenta and green, I believe. Might have got that in the wrong order, but that's the colours the game certainly uses. So that's what we're setting up there. Now, once we've done that, what we're doing here is we're clearing the user memory. We've got a fake LDIR command, that's a Z80 command. This is just clearing 256 bytes from memory address user RAM, and that's just to set the game to zeros. And then we run the main menu routine, which shows the main menu, who lets the player press fire, things like that. Now here is the main loop of the game. Now if I just start the BBC version up again, and if I just turn on the joystick, because it keeps turning itself off, and then we start the game here, I'll just discuss how the game logic works. Now if I press the right button here, you'll see I've turned right, but I've not moved any more. I have to release and press again to turn again, and that's so we don't collide into ourselves. Also, if I press the fire button, I start moving faster, and the counter in the corner goes down. That's boost mode, and that's so that the player can catch up with the CPU and makes the game a bit more exciting, basically. Now, the tick is used by boost mode. In boost mode off, the player only moves every other tick, and in boost mode on, they move every tick. Now, we've got a delay here, which is 5 if boost mode is off and 1 if it is on. We have to reduce the delay if it's on, because the drawing of the counter in the bottom with the vector font is a bit, unfortunately, slow. So that's what we're doing there. We're reading in the joystick here, and we are going to store the result in D here, ZD, which is a 0-page entry which simulates the D register on the Z80. Now the joystick reading routine is exactly the same as the Yquest one, so I'm not going to cover it again here. But what we're doing here is we're checking if any keys are down, and if they're not, we're clearing something called key timeout, and that's going to be used later. And if they are pressed, we store them in D, and we're going to look at that just here. Now, the first thing we're doing here is we're checking if the key timeout is 0, and if it's not, then we aren't going to process keys because the player hasn't released that key yet. So we're going to skip over, but if the player isn't holding that key down, we're setting boost to 1, which turns it off actually. Next, what we're doing is we're setting 0 page entry IX, which is a pair, to the address player X acceleration. Now, this is going to be used if the player is turning around. Now, if the player turns, we are going to decrease or increase player direction. That is the byte that defines which of the 4 possible turns the player is currently making. And then we are updating that with set player direction, which is going to copy the acceleration relating to that direction to the IX registers one here. So that's what's happening if the player is turning left or right. If the player presses fire, then we are going to check if the boost power is 0. If it is, then we can't accelerate. If it's not, then we turn boost on by setting boost to 0. Now, the actual processing of all those kind of things is done by handle player for the player, the human player, and handle CPU for the computer player. So those are in the multi-platform section. Now, when it comes to the graphics routines, we've got a clear screen here. The screen is starting from 4180 in memory here, which is why we had to move our game code, just get it out of the way. We've got wait for fire and read controls. As I say, if you want to see about those, please see the simple series or Yquest, which I covered those before. We're only going to look at the PSET routines here, and these are the drawing routines. Now, on the BBC and a few of the other systems, the screen width is 320 pixels wide. On some it's just 256, and so to allow me to use the same screen routines I'd used in the past, which used B and C in the 0 page, or ZB and ZC, to be an X and Y coordinate, well, 1 byte isn't enough for a 320 pixel wide screen. So I'm using A as the top byte in a pair, so A and 0 page B are the X coordinate and C is the Y coordinate, because I've got no screen bigger than 256 pixels tall. So we're doing that. And you can see I'm having to back up the X position here. Now, get pixel mask will take an XY coordinate and it will calculate a mask for the pixel within the byte of the screen that we need to change. So that's the first thing we're doing here, and this is going to calculate the pixel. Now, basically what we're doing here is we're moving the bottom 2 bits of the pixel coordinate, and that's because those will be the pixel within a byte. We are going to run get screen pos, which is our byte based function here, and that will calculate the memory address of the pixel we want to change. Now, that's exactly the same as it was before, so I'm not going to discuss it again, but it's basically just calculating a memory address that we want to write to, and it's calculating in HL. So HL will now be the byte address of the pixel, but we need to calculate the position within that byte that we need to change, and that's what we do next. So we get back A here, which is our X coordinate, and we take the bottom 2 bits that were ignored before, and these are the pixel within the byte. We then use a lookup, and you can see that just here, and these are the 4 possible positions of a pixel and the 2 bits that affect the color of that pixel. They're effectively a bit like bit planes. The nibbles here are the 2 bit planes for the pixels. So with getting that, and that's going to be the bits that we would need to write if we were setting the pixel, but we might be clearing the pixel. So once we've read in that byte, we're then EORing it, and we're storing the result in ZD. So ZE is now the byte to set the pixel, and ZD is the byte to keep the other pixels that we don't want to change and effectively clear the pixel. So we've now got all of the information we're going to need to change the pixel. So that's got the pixel position. What we now need to do is work out what color we're going to use. So we're doing that again. We've got a lookup for the bytes that will define a color. So this is color 0, all 4 pixels set to 0. This is all 4 pixels set to color 1. This is all 4 pixels set to color 2. And this is all 4 pixels set to color 3. And the combination of this, one of the bytes read in from this lookup table, and this lookup table will be the byte code that we will need to insert into our byte on screen to set that pixel in that color. It's a pain, I know, but that's what we have to do. So that's what we're doing. And at this point, we now have our color and we have our mask. So what we're doing here is we're masking our color, ANDing it with the pixel definition, and ZE now stores the byte that we would want to insert to set the pixel to the color we want to do. So now what we do is we read in the byte from the screen, we AND with ZD, which is the mask to remove the pixel we want to change. We then OR in ZE, which is the pixel that we want to change in the correct color, and that resulting byte can now be written back to the screen, and it will update the pixel with the new color for that pixel. That's all there is to it. I know it's a little bit complicated, and maybe there's easier ways of doing it, but this is the best I could do. It works okay anyway. Now point basically does the opposite. We're using get pixel mask again, which is again calculating the memory address, and it's calculating the mask for the pixels. What we're now doing here is we're reading in the byte from the screen. We're then masking it with the pixel that we're looking at, which now has the bits for that pixel. We then need to work out what color that actually is, and so we're using a command called byte to color map, and this takes a byte with a single pixel set and a position of that pixel, and it fills the entire byte with that color. It just does it by working out the position and bit shifting, and the purpose of this is to make the byte we read in the screen match one of the entries in our color lookup here, and it will now do so. So what we do now is we compare to that color lookup, and we can now find that, and the position within there will be the color 0, 1, 2 or 3. Now there is another way we could have done this. We could have shifted the bits out of that byte and then shifted them back together, taken the two bits from the bit planes within the nibbles and combining them together. That's not the way I did it here. You could do that, it would work perfectly well. I'm not sure which would be faster. This is very easy for me to port to other systems though, because all I need to do is change the color lookup depending on the layout of the screen, and it pretty much works the same. So I prefer doing it this way, but I'm not in any way trying to claim it's the best. I'm just trying to claim it worked for me. Anyway, that's how we're doing the screen drawing for this version of the game, and that's all we're going to be covering today. So there we go. So that's the BBC. As I say, it works pretty well. It wasn't too bad a port. The BBC version was pretty painless, relatively speaking, compared to some of the other systems, which is why it was the first one I did. So anyway, as always, if you liked what you saw today, please go to my website. There's documentation, the stuff you just saw on the website as well, so you can read through that. Maybe that'll help you out if I was speaking too quickly or didn't go enough detail for you. And also, of course, you can get the source code, and as I always say, you're welcome to use my source code in any way you can do so, including in commercial projects. You don't need to give me credit for it because I don't care. I hope you enjoy it and get some use out of it. That's the point of it. Anyway, if you've liked this video, please hit the like button, because that encourages YouTube to recommend it to other people. And if you subscribed, it would help with my motivation to keep making this kind of thing, so that would help me out as well. Anyway, I hope you've enjoyed this. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.